So my name is Brian. I'm a PhD student at the Redwood Center for Theoretical Neuroscience at UC Berkeley. And I'm going to talk about some work I did actually at Google Brain looking at unsupervised learning in more of a supervised context. And before I get into that, let me sort of explain what we believe the goal of unsupervised learning should be. And that goal should be is exposing high-level features from low-level feature data. For example, going from pixels to object identity. So finding a transformation or representation learning algorithm that allows you to go from low-level features to high-level, more semantically meaningful features. And traditionally, people have done this mainly through, for example, hand designing a cost function that doesn't require labeled data. So for example, in the Hinton and Slotkunov paper, they basically create a autoencoder and train this autoencoder with reconstruction error. And as they train this reconstruction cost, they hope that the encoder will create a representation that will be amenable for more supervised tasks. Additionally, people will also hand design features or properties that they want the representation to have. For example, they want the representation to be sparse. In the work of Olshausen and Field, they put a sparsity penalty on their training algorithm and show that the representation, when it becomes sparse, learns more edge-like detecting features that are, in future work, people have shown useful for more object-centric sort of tasks like detection and classification and other things. And lastly, people also just potentially hand design the update rule. As we saw in earlier talks, when people observe in neurobiology the postsynaptic and presynaptic firing timings and in relation to Hebbian plasticity, people create update rules that match those things that we observe in biology. So people hand design those aspects of updating learning algorithms as well. And what all these algorithms have in common is the fact that they all require hand design, meaning that someone had to do an educated guess about what the right parameters of that learning algorithm were and what the parameters should be. But the issue is that when you hand design something, often you might not necessarily get the exact answer you want. For example, when you train a variational autoencoder, as your unsupervised loss goes down, you can see that your goal loss, which is, let's say, few-shot classification with that representation of your encoder, it initially increases, but as you can see over time, it begins to decrease, meaning that there's a mismatch between your objective, which is unsupervised, and your actual goal, which is better supervised representations from unsupervised data. And this seems like it mirrors the past in terms of feature engineering, where people in the past for computer vision used to design features rather than learn them. But as we can see in the past 5 years or so, feature learning has become mainstream because it's a much more powerful way of letting the data speak for itself. So rather than allowing, let's say, a designer to design every single aspect of your model, you allow your model to have some flexibility. And this flexibility allows you to learn and let the data speak for itself and learn more useful representations that maybe the engineer wouldn't have come up with to begin with. And MetaLearning takes this idea a step further, where instead of engineering the learning algorithm, you actually learn the learning algorithm, meaning that you make your learning algorithm more flexible and you let data or potentially tasks govern what the learning algorithm should do. And to explain this a little bit further, let me explain the context of how we do this in terms of supervised learning. So in typical supervised algorithms, typically you have a model and a loss function. And typically this loss function is something like classification or regression, cross-entropy losses, what have you. And when you apply a learning rule, you update the parameters of the model by computing the loss, updating the model, and then computing the loss again and updating the model. So we call this the inner loop of our learning procedure. And the idea is that you just iterate this many times until convergence. And this is typically also standard in unsupervised learning, where you replace your loss function with a unsupervised loss function, as I mentioned earlier, and you iterate again until convergence. The difference is that meta-learning, when you apply this learning procedure, you actually have an outer loop. And the goal of this outer loop is to evaluate how well the inner loop did. So you do this through what we call a meta-loss. And the idea of this meta-loss is to basically evaluate how well that loop did internally in the inner loop. And once you evaluate how well it did, you can compute and potentially update your learning rule and reapply it again to the inner loop and repeat this procedure over and over again until you get a better learning rule. Now, we've actually all know about a certain meta-learning algorithm called evolution. And this is an example of meta-learning where your meta loss is, for example, your agent's fitness. So the idea being that when you evaluate your inner loop, you evaluate how well the agent did, you compute a meta loss, and the meta loss will filter through natural selection mutations, creating a better learning agent, and that agent just exists in the world and learns its environment, and then survives. And the idea is that you, again, compute the fitness of that agent, and you repeat the process of natural selection and loop over and over again. So from this standpoint, this is how we introduce meta-learning into unsupervised learning, where in unsupervised learning, we have in our inner loop a local learning rule that doesn't require labels, but we can evaluate it through the meta loss on supervised data. So essentially what we're doing is we're saying, let's run the local learning rule many iterations, and then after that, let's compute the meta loss on supervised data to evaluate how well that unsupervised learning rule did, and then update the learning rule. So through the outer loop, we're basically refining the learning algorithm over and over again as we update our local learning rule and then run our local learning rule over many iterations internally in that inner loop, and then we evaluate the learning rule on supervised data again, and then we apply gradient descent to update our learning rule to, again, go through the inner loop. Now, to give you more detail of that inner loop learning algorithm, now, it has flexibility, but it also has some structure. And the model that we're training in this talk is feed-forward neural networks. And in the green path is the feed-forward path with weights W1 and W2, and the feedback path is weights V1 and V3 and so on. And the idea is that these weights are not coupled. And what's nice about this algorithm is that we design our weight update to specifically be local in the sense that it only requires presynaptic and postsynaptic activations in adjacent layers to compute the update. And the idea is that we have a parameterized update that we can learn, and as we compute these updates, we only need local information within 2 adjacent layers. Now, both of these aspects make this model a bit more biologically plausible than backpropagation. For example, we don't need this weight symmetry property that backpropagation requires when training, and because we don't share our weights. We also only depend on, as I said before, the presynaptic neurons M and N to compute the weight update for weight connection M and N. But again, admittedly, there's also some non-biological properties of our model. And one non-biological property involves, within the layer, we actually compute extra information between units. And we do this specifically with the convolution operation within the layer. And also, we take measures to take terms and decorrelate the individual unit terms to compute the update. Now, these, while not being biologically plausible, do have, we believe, biological counterparts that we can replace. We don't believe that these components are very crucial to our model, and we believe that there have been previous work showing that you can replace these terms. Now, this is an example of when we apply our learning rule to the first layer connections of a feed-forward neural network. So this is like the first layer filters. And as you can see from left to right, we start with a randomly initialized learning algorithm that doesn't do much as you apply many thousands of iterations over the first layer weights. But as you go from left to right and you create more refined learning algorithms, you can see that suddenly it starts adding structure that's relevant to the data. So the learning rule actually starts having structure and starts learning and to extract information from the data set that the base model is being trained on. So you can see for MNIST, it actually learns something that you would imagine would be pretty useful for supervised classification with an unsupervised world, where it learns kind of like template-like aspects of digits. And for the CFAR data set, you can almost see the early signs of, on the right side, of edge detectors as we have this refined learning rule get better and better. And to more quantitatively go over these results, we describe our MetaTraining procedure where we train on labeled data sets, again, through the outer loop, on labeled data sets like CFAR10, glyph alphabet, glyph numbers, and ImageNet, and we apply our learning algorithm after it's been refined to unlabeled data sets, which are fashion MNIST and MNIST. So the idea is that we're transferring this learning algorithm from the MetaTraining procedure to evaluation time by evaluating on unlabeled data sets that we have. And this is the performance on few-shot learning. So after our unsupervised learning algorithm has created a representation, we apply one few-shot supervised layer afterwards to measure its performance in terms of how disentangleable are the class representations. And we can see is that our model, the blue line, is fairly competitive with things like the variational autoencoder I mentioned earlier in terms of creating a supervised representation that is useful from an unsupervised learning algorithm. Now, we also show in supervised learning, which is if you didn't have any of the unlabeled data and you only applied the labeled data to it, we still outperform those algorithms, meaning that our algorithm is actually making use of the unlabeled data in a way that's non-trivial. And now we're going to evaluate our learning rule, since it's local, on changing the architecture. So we train on feed-forward neural networks that are between about 2 to 5 layers and about 64 to 512 units. And we try to apply our learning algorithm to much larger networks, which are up to 11 layers and up to 10,000 units. And we can see, actually, in these plots, when you measure the increasing number of layers, is that when our learning algorithm is refined, the blue line, it stays the same in terms of when you increase the number of layers or increases slightly in performance. But if you had a learning algorithm that wasn't trained, which is the green line, as you increase the number of layers, your actual performance actually degrades, meaning that our refined algorithm is actually doing something relevant to the task and generalizing to larger number networks that it hasn't been trained on. And then we also try increasing the number of units. And again, we see that the network that is trained is actually doing substantially better than the network that isn't trained in terms of increasing the number of units. And we believe that this is mainly caused by the fact that we have local learning rules that can be applied between every pair of units between 2 adjacent layers, meaning that it can be easily extrapolated to many larger networks because that local learning rule is the same rule applied to every single pair of nodes between 2 layers. So I think this is early signs that our learning algorithm is actually learning something useful, which is the idea of unsupervised learning through this MetaLearning framework. And with that, I'd like to thank my collaborators, mainly Metz, who did a majority of the work I showed you here today, and Niru and Jascha, who were very helpful and very inspirational for the ideas in this project. And I think Niru's in the crowd, so if you have questions, you can also ask either me or him. And with that, I'll take questions. Thank you.
Thank you very much. We have time for a couple of questions.
Thank you very much for a very interesting talk. So what are the crossover learning rules you allowed? Like the correlation or including non-linear terms?
Yeah, so there was a lot of nonlinear layers in the actual transfer from the pairwise activations to the actual weight update. It's essentially like a neural network that has multiple layers.
So how many parameters did the learning rule have?
Since they were convolutional, not too many, but it was sort of many layered, I would say. I don't remember the exact count, but it wasn't too many.
And the resulting the learning rule, how did they look like? Something like a Hebbian learning or totally different?
We can't comment on that yet because we haven't done a full analysis on that. We're still actually adjusting that model. And the issue is that model is fairly complex right now. So I would say that this talk is more of a framework that we should work in terms of designing our rules rather than saying that we discovered the learning rule that we should sort of investigate now, because I think our performance could still go up from this point.
Thank you.
Hi.
Hi.
So one way to motivate unsupervised learning is that you don't know in advance what kind of task you will have to perform.
Right.
Whereas supervised learning is obviously task specific. So I was wondering whether there's a way to include this aspect of, I want to be able to perform on several different tasks well in your MetaLearning.
Yes, so
paradigm.
we actually did notice an issue where potentially it could throw away information given that it learns a representation that could be specific to a supervised task, but not necessarily your supervised task. And what we have done right now is we're extending the model so that we're actually mixing in auto-encoding, requiring it to preserve all the information in the representation it creates. So hopefully it creates a supervised representation that's good for a lot of tasks because it preserves information.
One last question.
Yeah. Hi. So in the forward pass, you were sending down the neural activity. It wasn't clear what signal was being passed down in the backward pass.
Could you say the last part again?
What signal was being passed down on the backward pass?
Oh, it's just a signal that's generated by each local learning rule to pass down almost like similar to backward but delta function through this V matrix that's learned.
Okay.
I can give you more details offline if you.
Okay, sure.